to our senior string theorists who is going to share their experience during the first and second string revolution and their vision about the future of string theory. So let me try to introduce those three speakers. And I just realized when I was doing the Wikipedia and looking at their CV, it's one of the I just realized all of three speakers, they have to have a strong correlation with the Nobel Prize. So let me first introduce Professor Cliff Burgess, who is currently a professor in McMaster and also at the Parameter Institute. And I think Cliff did a PhD in UT Austin with Nobel Prize winner Steven Weinberg. And then after a short stint of postdoc in IIS Princeton, then he moved to McGill and rise through the rank from assistant professor to a full professor, and then later move on to McMaster. And Cliff is interested in string phenomenology, cosmology, and also, of course, in condensed matter as well. So the second speaker today will be Professor Sumit, who is currently at full professor at the University of Kentucky, and also has briefly taken on the position of the chairman of the department. And Sumit did a PhD in University of Chicago with on a Nobel Prize winner, Nambu. And after with a postdoc from Fermilab and Caltech, and he moved to, I think you were in Tata for some time as well, right, as a faculty. 17 years and faculty in Tata. Then he moved to Kentucky to be a professor there. And finally, we are actually, I think, especially honored to have Professor Chung-I Tan, who was originally hailed from Taiwan and moved to U.S. when in his teenage year. And then he did an undergrad in Berkeley and PhD at Berkeley as well with Professor Jeffrey Chu, and one of the original founder of S-matrix, who later, of course, this idea of S-matrix play a very important role in developing string theory. And then Chung-I, I think he was briefly in Princeton, and then moved to his current position in Brown, and recently he was the chairman of the department as well. So I think today's order of speaking will be, I think Chung-I will be telling us first, and then I think, is it Cliff or is it later? It's okay, either one, Cliff or Sumit. And then I think the point is really for students, it's meant to be informal. So I do want more and more students asking questions and ask those senior experts to share their insight and vision. I think that's the purpose of today's exam. So let's welcome Tony to give us this talk.
Okay, well, this is an honor to be here and leading off, and mentioning my seniority, and I'm the most senior around here, so you will allow me to start, so I will spend the time saying nothing, leave all the insight to the others to convince you about the future of string theory. Now, what I have here is a listing about what's so-called first string revolution and the second string revolution. And of course, there more to it than, oh boy. Then there's a period before that, which I'll call pre-revolution, I guess. And this is a period where I started being a student and enjoyed the activities very much. And if you want to go back before that, it would be and we all know that period very well. And it's of course it's more recent period, probably more. Oh boy. Yeah, never mind. I think they will want me to do something. How do I kill this?
Just this.
I have to figure out how. I lost my arrows. Go back here. Having remind you about what has happened in the past, perhaps the most interesting thing is what's going to happen to the future. Okay. So I will say a few words and then make a prediction about what's going to happen. Now, we're almost familiar with what's happening now, and all kinds of things has taken place over recent years, and each stage some important work is being done, and it's so important that we call it a revolution. Of course, this whole dividing the history into all those parts is somewhat artificial things and stuff, and we build one thing upon the other, and of course, if you're a young person who did some important work, you would say whatever happened in the past were all wrong, and we will set this new direction and in the future. So, for instance, there are all kinds of buzzwords at a given time, which is important. So, right now, we all heard of the NTU-CTP, because that's the most important work, and what's going on. Those of us trying to borrow this and try to carve out a little work and try to explore the future about what's going on. And, of course, this whole idea involved here is it's new, but in a way, it's nothing but trying to have some unification. Unification, we now know string theory is just like gauge theory. Gauge theory is just like gravity, and there's no such distinction. And in the course of doing that, we also want to think deeply. We ask what we think about what is space, time, new quantum principles. And in the course of doing that, we try to show our technical power. We start studying amplitudes, we explore analyticity, unitarity, bootstrap, and all this kind of powerful technique to help us. In the course of doing the calculation or analysis, we may find that we have to go back, re-examine our understanding what is space and time, what is locality. In a way, that's how progress is made. And there's some seemingly trivial concepts as you're exploring new phenomena require you to go to re-examine the new accepted concept. If you're lucky, you happen to do one which turned out to require to enlarge our previous understanding and the progress. Now, of course, we can ask the question, what happened before in the pre-revolutionary period? Well, actually, we were also trying to find a relation between string theory, gauge theory, and gravity. In fact, we said they were distinct, and gauge theory are useful. Yes, useful for understanding QED, and perhaps it's useful to understand weak interaction. But when it comes to strong interaction, since we didn't have QCD at the time, and what was just being formed, we thought perhaps it was a string theory. And the gravity, of course, is kind of thing. When I was a graduate student, was to stay away from that. Okay. And in the course of doing that, we also start examining the notion of space, time, what is locality, question about quantum principle. We study amplitudes, we study analyticity, unitarity. We even study use concept, bootstrap, and analysis. So, in a way, the so-called pre-revolutionary period was back to the future. We sort of knew what was coming and into what is now. Of course, what is now, we said string theory, gauge theory, or gravity are the same, and in a way related. And we start questioning what is space, what's time, and what is time. So history has a way of repeating itself, but in every stage, when we look at the same problem from a different perspective, and we learn something. So let's come back to the second string revolution. And as I said, in a way, the key concept here is student use of NTU-CTP, we have begun to provide unifications. Of course, unification is always a dream of everybody, and we study and the question using different techniques. Often the techniques are the ones which have been tried before. So in a way, the second revolution is also a renewal of something old. But something old which is, again, somebody's telling me to shut up. So,
sorry, doesn't seem quite engaged this way.
So in the course of in the last couple of years, all kinds of exciting work's been done, and there's a consequence of the second spring revolution. So this then brings me to the question: what's going to happen to the next post-spring revolution of the recent time? Okay. So. Having seen this going on, for some people like me, engaged in the early part of the so-called pre-revolution, then first revolution, and second spring revolution, I think for the benefit of young people, I can safely predict that we'll have more revolution. And then what kind of revolution? Next speaker was telling me what's going
So Sumit has bravely taken on the challenge of describing the more revolutions.
Actually, more revolutions.
Oh yeah, we can talk about it.
Those are my dogs. Another dog. And my wife. Last one. Okay, so what I'll do is I'll try to. It's a strange talk to give. So what I'll try to do is try to recount my own experiences of this project. So I started my graduate school basically in 1980. I was a student of Nambu, who's one of the fathers of string theory. He asked me to study string theory. I said, why? Why should anybody be interested in string theory? We have a theory of QCD, so I think that's good enough. So I didn't listen to him. I think it was okay. I think at that time it was not very interesting. So I should to give you a little bit of a background, the kind of activity I was exposed to. This is a very personal account. There were two strands of activity in this general area of particle physics as far as I could see when I was in graduate school. There was one strand of activity which was very motivated by QCD. Confinement was one of the premier problems of the time. Larry's gauge theory had just arrived on the scene. The kind of physics which people were studying to do that were more akin to statistical mechanics and condensed theory than conventional particle physics, and I was sort of basically trained in that kind of tradition. So the kind of things which we were hearing at that time, which was coming up, was large N expansion. That's what I did in my PhD in. There were things called loop equations. Loop equations were equations which were supposed to be satisfied by Wilson loops. There was a proposal that the Wilson loop should be the string fields. I mean, the idea was to derive string theory from QCD. And then there was Liouville theory, which I'll come to a little bit later. There was another strand of activity going on at that time, which was a motivation from unified theory. It was based on trying to unify all the fundamental interactions. One of the most powerful ideas was supersymmetry, supergravity and grand unification. It was a bit unfortunate that the practitioners of the two different strands seldom talked to each other at that time. But that was the fact. There were very few people who would sort of straddle between the two things. And I call there were string revolutions -2 and -1. I think -2 was dual resonance models and the emergence of string theory. I forgot what I mean by number 1. Okay, so right around the time I started, Polyakov wrote two seminal papers, 2 physics letters, 2 pages each, which sort of laid the foundations of modern string theory. The motivations for those papers was, as far as I could see, not too much of trying to unify strong, electroweak, and so on and so forth. Though one of the papers was on superstrings, not superstrings, but wall sheet supersymmetry. But I thought the motivation, at least as I could hear, is that now we know how to do string theory in 4 dimensions, because formulation in terms of Louisville theory, and in fact, as I was studying in my PhD time, there was a lot of talk about that. Maybe this can be done. Of course, it's wrong. But it did inspire new approaches to derive Young-Mills strings based on loop equations, Eisenhower equations. Matrix models arrived on the scene. As models for large N theory, Eguchi-Kawai models. Meanwhile, Green and Schwartz was making this momentous progress in superstring theory, which these people were not really listening to. Almost very few people were listening to. Okay. String revolution number 1, I call, is in fact two major developments. The first was Milavin Polyakov's homological, the discovery of conformal field theory, which I still believe is one of the most permanent contributions of string theory. It may not have anything to do with strings, but it came out of string theory, and it's a permanent body of knowledge, which I think will remain hundreds of years from now. It's interesting, something else. My God. Interestingly, it arose out of attempts to solve Louisville theory. Louisville theory is a special conformal field theory which they tried to solve. They couldn't, so they invented this entire technology of conformal field theories. There was a lot of excitement in Chicago at that time when these papers came around. I was just about to leave graduate school because Friedan just came back from a trip from Moscow. He had talked to Polyakov for several days. He came back and gave a series of 3 talks, I remember, which was called On Polyakov's Formulation of Conformal Field Theory. This was before this paper was written.
So Polyakov was already some hidden superstar in Russia?
He was a hidden superstar everywhere.
Oh, okay. He was just hidden in Russia, that's what I meant.
Yeah. And Friedan himself was one of the people who was trying to work on Louisville theory. He made some big progress in Louisville theory earlier on. At the same time, Green and Schwartz discovered anomaly cancellation. And that was, of course, the major effect. But that was also the time when members of these 2 communities which I talked about, who were not talking to each other, starts talking to each other. And so there was some tremendous development, and there was another class of people who decoupled from the development because of this. That always happens. So what followed was quite interesting. It was rapid progress in world sheet formulation of string theory. There was rapid progress of whatever you can call string phenomenology, sense compactifications, and I think another permanent body of knowledge was the mathematics which came out of it. The mathematics, of complex geometry and algebraic geometry which came out of it. I think that was quite stupendous. There were D-branes, which was actually discovered independently by Polchinski and Horzava, but that was sort of on the fringes, because the idea was closed strings to describe everything. Who talks about open strings? That was not. Heterotic string theory was the thing, and so people were not paying much attention to D-branes. 88 to 91 was interesting. because it sort of diverted a little bit for a brief period of time, little bit diverted the attention of the community to slightly different thing. It was again another very interesting and possibly momentous paper by Krishnish, Polyakov and Zamolodchikov, who managed to solve Liouville theory in certain circumstances as theories of non-critical strings and as well as theories of random surfaces. And that again brought back the idea that maybe now we can do string theory in low dimensions. Of course, it didn't go very far. It didn't go very far, but it did lead to something which became very important to the beginnings of what is called nowadays called the holographic correspondence. I mean, yeah, it sort of brought together some ideas about large N theories which sort of large N degrees of freedom organize themselves as dimensions into a new framework. So I think that was an important discovery. It's also considered to be, after this thing happened, it was very short and it was a very lean period in string theory. And everybody said, oh, what's happening? Nothing is happening in string theory. So people started thinking about something else. And one of the things people thought about was black holes. And that was good. A lot of confusing papers were written about black holes. Black holes, it was inspired by the fact that people found black holes in 2 dimensions. Again, a thing from non-critical strings. Strominger was one of the persons who wrote a lot of what is now considered wrong papers in black holes, but it paved the way to the next big thing in string theory. Because it's the first time I think particle theorists started thinking very, very seriously about black holes and the information problem. So that's what I said. Meanwhile, around that time, there was another development that took place, which became important later on, was an acute observation by Tuft and Susskind, which came to be known as the holographic principle. That paper was written in 1993. There was not much meat to it, except that the idea was, quite interesting. Susskind proposed black holes as balls of strings, and why don't we count the number of states in the black holes? There was quite a prophetic paper he wrote, which had a footnote, which said that maybe if you look at extremal, I think the footnote said that Kumun Vafa pointed out that if we look at extremal black holes, supersymmetry might allow us to count the microstates. I think that was quite interesting. 94 to 97, a lot of things happened. Duality in gauge theory, the work of Sen and Seiberg and Witten. M theory came, the unification of strings. D-branes emerged as a key element in our whole understanding of string theory. One understood a lot of things about black holes, particularly entropy and Hawking radiation. There was matrix theory, the ADS-CFT correspondence, and this new set of ideas in what you can call non-perturbative string theory brought in new hopes for phenomenology in the form of flux compactifications. So the few years after that, applied ADS-CFT begins, goes back pretty much like what Chung-I said, go back to the roots. Maybe one can understand QCD after all. Just heard a talk by Chung-I some time ago that it's actually quite useful to understand QCD. And the beginnings of application to condensed matter inspired models started. So what happened to string theory as the theory of everything? I think that suffered a blow precisely because of these developments. I think it was clear for a long time that there doesn't seem to be anything wrong with 10-dimensional Minkowski space. Everybody was ignoring that with the hope that if one understands non-perturbative string theory, somehow that will go away and we will somehow land up with a more realistic compactifications as one of the unique solutions. But I think the work on flux compactifications and the work on the landscape of string vacua basically gave a blow to that philosophy of thinking. I think it's fair to say one doesn't know what to make of this. If you are a strong optimist in the subject, you would think that something is wrong with all these developments and one with one. Nobody has found out what is wrong about these developments. My personal belief is it's here to stay. I think it's, and there are in fact huge number of string theories. And the word theory in string theory should be interpreted pretty much like the word theory is interpreted in quantum field theory, rather as in Weinberg's alarm theory, namely not a model for the universe, but a bag of conceptual tools and methods which can be applied to a wide variety of problems. That's at least my personal opinion of what will happen. Till present, I think it has been dominated by applications of ADS-CFT. We have a more refined understanding of black hole microstates and very interesting offshoots in the forms of integrability and scattering amplitudes that sort of emerged. So finally, the future, I suspect that the holographic principle will continue to provide interesting insights into phenomena of strongly coupled gauge theories. It's very unclear to me how much of string theory is really needed in this. I think maybe we have transcended string theory and obtained something more basic. I don't quite know. So far as string theory is concerned, I think we probably agree that most of the beautiful results and the quantitative success is heavily dependent on supersymmetry. I mean, supersymmetry is like a shackle which sort of holds us down. We try to go out of it, we never succeed. So I believe that the next revolution will depend on the development of theoretical tools which do not depend on supersymmetry. Because I think that's what is holding us back in many respects. And so maybe we need to go back to formulations of string theories in non-trivial backgrounds. There are very few people who are actually working on string theory at the moment. But I do see a sort of revival of interest into string theory as a worldsheet theory. I think good, serious people probably should do that. Maybe something will come out, but who knows? I wouldn't make any prediction.
So this will be the short part. I was kind of taken aback at being asked to tell stories about history because I didn't feel that old. But it's true that these revolutions took place, and I remember living through them, and I'm not really a string theorist is the other thing that you should know when you hear what I have to say, because I've kind of bounced off string theory a couple of times, and the first time was in the first revolution, because I was a graduate student that I graduated in 1985. And I can remember I used to go to, at the time where I was studying, it was the second of the classes of people that weren't talking to each other in Sumit's talk. And people were thinking about supergravity and fluid-defying theories, and could you unify things in those theories. And it was becoming more and more clear that it wasn't going to work because there was a real problem with anomalies, and that either you didn't have chiral fermions or you didn't have consistent theories, and it all seemed like it wasn't going to work. And an independent line of development, as a student, I used to go to colloquia with the idea of seeing whether or not you get somebody who's an expert in the field, and if they couldn't sell it to you, then I didn't want to learn it. And so I remember going to Roger Penrose gave a very nice colloquium about twistors. I remember thinking, that's all very beautiful, but I don't need to know that. That's not going to be useful for any physics. And then shortly after that, John Schwartz gave a colloquium on string theory, and I remember coming to that one thinking, that's also very beautiful, but I don't need to know that either. That's not going anywhere. And he gave a seminar, and all the people, like Weinberg and Polchinski, were giving him a hard time. He said that it was a finite theory of gravity, and they didn't believe him. And so I remember thinking that's all very nice, but I don't need to know string theory. And it's true that I was probably one of the last years to graduate that you could afford to know no string theory, because in 1984,